Hi, welcome back. So now we are ready to generate Aries test functions, and the idea is very simple. So let me point out the basic thing. Every general polynomial of Aries test function, polynomial of order n, is given by this. Real part of x plus iy times a plus ib to the z to the n minus 1 plus c plus id to the z to the n. A, B, C and D are arbitrary constants. This is the most general Aries test function you can come up with. That's all. Basically, Fz is this, Gz is that. So if you have pick n equal to 2, n equal to 3, n equal to 4, n equal to 5, you can generate, keep generating. That's all. You will get all of them. There is nothing more to it. Right? And we can do. So this kind of Aries test function can solve the problem that is shown below. That is, I have a beam, I have some distributed loads on both sides, and I'm going to have weak boundary conditions. So strong BCs here and here, weak BCs here and there. Okay, so anything that's like that, we can solve. Strong, weak. So anything like that, we can solve. So how do you go about solving that? We are going to specify the top and bottom as polynomials as long as the strong boundary conditions So what do we have to do? A of xy is some summation n equal to 1 to capital N, whatever we want to do. Real part of x minus iy times an plus ibn times z to the n plus, let's make sure we have the right thing. So let's see what does the form look like. Sorry, z to the n minus 1 and z to the n. Z to the n minus 1 plus cn plus idn z to the n. So you do this Aries test function. You don't even have to check. Don't have to check. Del squared of del squared A equal to 0. You don't even have to check that. Sigma xx will be a comma yy. Sigma yy will be minus a comma xx. Sorry, a comma xx. Sigma xy will be minus a comma xy. Displacements you can find. Only thing you have to do is just match boundary conditions on the strong side. And weak side. Your whole task is pick a value for n. So pick a value for capital N and then find the boundary conditions, and that's the end of it. That's all. It's painful, but it is, we have converted a problem that looks like almost impossible to solve into something that's really boring. So I'll show you what I mean. Okay, so first thing is you can create these Aries test functions, and I have shown you. So this is the second order Aries test function. This is A3, A4. Basically I just expanded it. You can see the formula here. In fact, you can expand it and you can write it this way. And by the way, if you write it that way, it's called a Papkovich vector. You don't have to worry about the names, you know. It's probably not Papkovich, it's probably one of his graduate students. You know how it is, right? So it's not, so don't worry about the names, but you can see I have generated several of them. You can pick and you can mix and match, so that's not a big deal. All I want you to understand is I generated all of this by using this expression and plugging in n equal to 2, n equal to 3, n equal to 4, n equal to 5, n equal to 6, n equal to 7. You can keep generating, that is capital N, right? You can keep generating functions of any order, and you can see, okay, so that's not a huge deal. And then you can mix and match. If you have Mathematica or Maple or something like that, you can mix and match. This is very easy to do. By the way, just to show you, I've gone all the way up to 7. Okay, you'll have to think about how this is organized. So there is some sequence here, and there is some symmetry and anti-symmetry and all of that, so that it makes our life easier. But don't worry about all of that. All I want you to understand is all these Airy stress functions can be generated. Now the question is, what should be the order n? So remember, it was summation n equal to 0 to capital N. What should I pick for that? Okay, so it depends upon normal tractions. The order of the normal tractions should, if the order is m and the highest power of the shear tractions is n, then you should contain all polynomials up to n plus 5 and m plus 4. Why is this m plus 4? Because I have to do 4 derivatives. So that's why I have to increase it by 4. Why is it n plus y? N plus 5 because of cross derivatives for shear stress. That's how it works. So max of m plus 4 n plus 5. So normal stress and shear stress. Okay, at the top and bottom, strong boundary conditions. Then you're done. So let's look at an example. Here it is. Look at that. Normal stress uniform, which implies order is 0. Shear stress 0, order 0. This is a 0th order polynomial, no? So max of 0 plus 4 comma 0 plus 5 will give me 5. So I have to pick Airy stress function which is up to 5th order. Okay, that's my Airy stress function, is up to 5th order. How did I get this? I will show you. I got this by going to my table and picking everything up to 5th order. There, all these things up to 5th order. Okay, that's all I did. It is kind of painful and you get lots of constants. Look at how many constants are there. Okay, that's first order. That's second order, third order, fourth order, 5th order. So you can say I have lots of constants. Okay, now what are you going to do? How are you going to, you got to calculate something like 15, 16 constants. Okay, so what are you going to do? You are going to calculate these constants by matching the boundary conditions. And this is where you have to be clever. That is, don't be stupid in trying to blindly match all the boundary conditions. Look at the boundary and see if you can exploit symmetry. So this is the condition, exploit symmetry. What do I mean? Notice it's symmetric about this line. This side and that side are the same. So I want to make sure that that is met. So if that is the case, if it is symmetric about the y-axis, Airy stress function can contain only even terms in x. Otherwise, it will not be symmetric about the y-axis. The stresses will not be symmetric about the y-axis. So how do you get it to even terms in x? So look at all the things that have odd terms in x and drop them. So if you do that, you will see that my Airy stress function is quite a bit simpler. Then apply the strong boundary conditions at the top. So I am doing that. Strong boundary conditions at the top, and this has to be true for all. So sorry, this has to be true for all x. That means each of these terms each of the coefficients of x must be 0. So you look at that, that will give you two conditions. Okay, and it's not an equation for x. So you are going to get a whole host of conditions. Notice that there are terms which have x cubed, so there are terms which are linear in x, which are coefficient of x cubed must be 0, coefficient of x must be 0, all kinds of things. And so there are 4 conditions. You apply that and you will get a whole bunch of constants. If you have all these constants, you can see that I can dramatically simplify it. This is where your ability to do some algebra comes. So if you simplify it, you will finally find that area stress function looks very nice. That's how the area stress function works. So you start out with the general polynomial, look at the equation, see if you can exploit symmetry, and once you can exploit symmetry, you can solve this and you can calculate the stresses and you can calculate the resultants. The resultants will give you the equations. You can read it, I don't care about it, I want you to read it, and you can calculate what are the constants. Once you do that, your area stress function looks like this, and you will see that this part is what you get from beam theory for the stresses. These are the corrections from elasticity. This is beam theory, and these are the corrections from elasticity. Okay, so you can take a look at it, and you can do contour plots. So what it tells you is there is huge bending moment here, which becomes shear stress on this side and that side. So if I plot this, you can see normal stresses are very high in the middle, because the simply supported beam, so the normal stress is going to be very high in the middle and not so much in this other part. And you will also see this very interesting flow of stresses from the top towards the bottom. Remember, this bottom had no stress, no traction, top had traction. So what is going to happen is it's got to go flow to the sides. The traction cannot go through here because this is like an impermeable wall for tractions. It cannot flow out. So you will see it has to flow through the sides. That's how it works. Please read this thing very carefully because you will understand a lot more about this when you look at the details. Thank you.